everyone, thank you so much for joining me for this video. Here are today's learning objectives. So the first is to be able to draw and interpret titration curves using all combinations of strong and weak monobasic acids and bases. And then we're going to select suitable indicators using titration curves and appropriate data. The next is to understand how to use a weak acid strong base titration curve to demonstrate buffer action and to determine Ka from the pH at the point where half the acid is neutralized. And then finally, we're going to look at a core practical, which is finding the Ka value for a weak acid. Now we're going to look at some definitions. The equivalence point is a point in a chemical reaction when there is exactly enough acid and base to neutralize the solution. So for example, in titrations, when you're adding an alkali to an acid, it's when you add just enough alkali to neutralize that acid. The endpoint is the volume of alkali or acid added when the indicator just changes colour. And half neutralization is when the acid has been half neutralized. And so it is the point at which the pH of the solution is equal to the dissociation constant pKa of the acid. And we know this because of the formula pKa equals pH minus the log to the base 10 of the concentration of A minus over the concentration of the acid. And because of this, we know that the acid is exactly 50% dissociated when this ratio of concentration of A minus over the concentration of HA equals 1. And that's when we get the pKa is equal to the pH. Now we're going to look at titration curves. And these are curves that we can get from titrating acids with bases. So the first one we're going to look at is when we titrate a strong acid and a strong base. So we've started off with the strong acid and we're adding the strong base to it. So that's why the curve starts off at 0 because it's a strong acid. So the pH is very, very low. And then it gradually increases as we add the strong base. At around 25 centimeters cubed of sodium hydroxide added, the pH dramatically increases, and we call this point the equivalence point. So if we drew a line straight down, then this would be called the equivalence point. And that is the point where we've added enough alkali to neutralize the strong acid. We can also tell that it's a strong base that's been added because the end of the graph where the pH levels off is around 11-12 pH. So we know it's a strong base. The equivalence point can also be called the end point. They're very, very similar terms, so they can be interchangeable. The second curve we're going to look at is the strong acid weak alkali curve. And so we started off with the strong acid and we're adding a weak alkali to it. And so the pH starts off very, very low until about 25 centimeters cubed of the alkali has been added. And again, this is called the equivalence point. The curve ends off around a pH of 8, which indicates that it's a weak alkali that has been added. So the third curve we're going to look at is a weak acid strong base curve. And so we've started off with a weak acid, and that's why the pH at the start is a bit higher, so it's around 3. And then the pH increases gradually as we add the strong base. And again, this time at around 24, we then get the equivalence point where the pH increases significantly. And then the pH levels off at around 12-13, indicating that it's a strong base. What we can do with this curve is that we can find out where half neutralization occurs. So half neutralization is when half of the acid has been neutralized. And so because the equivalence point is at 24 centimeters cubed of alkali added, that means that the half neutralization point occurs when the volume of alkali added is half of 24. So it would be at this point here at 12. And so we would draw two straight lines, and it's about 5, the pH. And so we can say that half neutralization occurs at 12 centimeters cubed. And we know that at half neutralization, the pKa is equal to the pH. And so the pH we read as 5, so that means that we know the pKa is 5. And so we can work out the Ka value because we have the formula pKa equals minus log to the base 10 of Ka. And so Ka will be equal to 10 to the power of minus 5. And so that gives us 1 times 10 to the minus 5 moles per decimeters cubed. So we found the Ka, so the dissociation constant of this weak acid. And we can also call this region here the region where it acts as a buffer. And that's because there's very little pH change with more alkali added. And so because the pH is maintained, we call this acting like a buffer. So the last curve that we're going to look at is this weak acid, weak base curve. So the pH starts off a bit higher at 2 because it's a weak acid, but there is no sharp increase in pH. And therefore, we can't titrate a weak acid and a weak base because it's very difficult to find a suitable indicator to tell us when this equivalence point endpoint is. And we also know that it's a weak base that's being added because the pH, when it starts leveling off is around 9. And if we wanted to add the acids to the bases, all of these curves would be flipped round pH 7. So now we're going to have a look at some indicators. So suitable indicators should have these 3 properties. The first is that the colour change must be sharp rather than gradual at the end point. So that is no more than 1 drop of acid or alkali is needed to give a complete colour change. And an indicator that changes colour gradually over several cubic centimetres would be unsuitable. And this is because it would not give a sharp endpoint. Secondly, is that the endpoint of the titration given by the indicator must be the same as the equivalence point, otherwise the titration will give the wrong answer. So the endpoint is the volume of acid or alkali that you've added before the colour changes, and the equivalence point is how much acid or alkali which has been added so that it has been neutralized. And so these two should be the same. Thirdly, is that the indicator should give a distinct colour change. So, for example, the colours to pink change of phenolphthalein is easier to see than the red to yellow of methyl orange. So now looking back at the 4 curves that we have, starting with the first one where we have a strong acid and a strong base, you can see that both of these indicators are suitable because they both change colour where the sharp increase in pH is, so where the equivalence point is. At 25 centimeters cubed. However, phenolphthalein would probably be more suitable because you can see the colour change more. For the second curve, the weak acid and the strong base, you can see that only phenolphthalein is suitable because methyl orange changes colour before that equivalence point. So that won't give us an accurate indication as to when it has been neutralised. For the third curve between the strong acid and the weak base, the opposite is happening. So methyl orange is more suitable because it changes colour actually when the equivalent, compared to phenolphthalein, which changes colour at a pH which is too high. And so when it actually becomes neutral, phenolphthalein won't change colour until it's more alkali. And for the last curve, between a weak acid and a weak base, both of the indicators are not suitable because they change colour either at too low a pH or too high a pH. And so that's why we can't really titrate a weak acid and a weak base, because we can't tell when the endpoint is. So now we're going to look at a required practical, and it's to investigate how pH changes when a weak acid reacts with a strong base and when a strong acid reacts with a weak base. So the example we're going to look at is with ethanoic acid and sodium hydroxide. Ethanoic acid is the weak acid and sodium hydroxide is a strong base. So our method is split into two steps. The first part is calibrating the pH meter, and part two is the actual measuring of the pH of the mixture of acid and alkali. So for part one, first thing you do is rinse the pH probe thoroughly with deionized water and shake gently to remove the excess water. And we then place it into a standard pH 7 buffer solution. And then we record the pH, because the pH meter will be close to 7, but it might be slightly off. So we need to record that pH that it's measured. And then we repeat for pH 4 and 9.20 buffer solutions. So we have a recorded value of the pH for an acid and an alkali. And then we plot a graph of the pH of the buffer solution over the recorded pH reading. And this is so that we can obtain something called a calibration curve, where it'll help us in part two when we've recorded the pHs, and then we need to use this calibration curve to find out actually what the pH is when we shift it along slightly because of the inaccuracy of the probe. And so for part two, the first thing we do is rinse a burette with 0.1 moles per deciliters cubed of ethanoic acid, and we make sure to fill this all the way to the bottom below the tap and that there are no bubbles. And then we transfer 20 centimeters cubed of this acid to a clean beaker, which is 100 centimeters cubed. And then we rinse a second burette with the same 0.1 mole per deciliters cubed, but of sodium hydroxide this time. And again, we fill it up right to the bottom without any bubbles. And then we rinse the pH probe with distilled water and clamp it so that the bulb is fully immersed in the beaker, and use a rod to stir the solution gently and record the pH of the acid. And then we add 2 centimeters cubed of sodium hydroxide to the beaker using the burette, and we stir the mixture gently and record the pH. And we repeat this until we have added 18 centimeters cubed of sodium hydroxide. And then after that, we take pH readings every 0.2 centimeters cubed of sodium hydroxide that has been added until 22 centimeters cubed has been reached. And then we take the readings every 2 centimeters cubed added again until 40 centimeters cubed has been added. So the diagram on the right is of a normal titration, but the setup would be like this, but with a pH probe and using a beaker instead of a conical flask. So in the burette at the top, we would have the sodium hydroxide, and in the beaker at the bottom, we would have ethanoic acid and the pH probe, and probably a stirring rod. So then after we've done the experiment, what we should get is we should firstly have the calibration curve. So that will be on the Y, we would have the pH of the buffer solution. And on the x-axis, we should have the recorded pH by the pH probe. And so we had 7, which I'll put here, and then 9.20, and then 4. So at 4, the recorded pH might not be 4 exactly. It could be, let's say, 4.2. So then we would mark on the value of it. So we would plot that. And then for 7, maybe it was 6.9. So then we would plot that. And then for 9.2, maybe it was 9.24. And so we plot that, and then we draw a straight line through these, and that will be our calibration curve. So then when we actually use the pHs that we recorded in the part 2, we can adjust the pH according to the inaccuracy of the probe. And then what we do is we plot a graph, another one of, on the y this time it will be the adjusted pH. So after using the calibration curve, what the pH value is, and then we have the volume of sodium hydroxide added. And your curve should look something like this. So it should start off as an acid, so maybe around 3, and then it should be a slow rise, and then we have a straight line here, and then it levels off at the top. So at the end of it, there's no dramatic increase in pH because we call this the end point, and there's a surplus of H+ ions. And we call this point here, where there is a dramatic increase in pH, the equivalence point. Or the end point. And we can also work out the Ka of this weak acid strong base experiment. And how we do this is we take the equivalence point. So say the equivalence point is at 25 centimeters cubed of sodium hydroxide added, just as an example. Then what we would do is we would draw a line up to the curve at half of 25, because this is where half neutralization occurs. And so we have that at 12.5 centimeters cubed of sodium hydroxide added. And then you draw a line to the y-axis to find the pH at that point. And so say the pH comes out to be 5. So to find the Ka, you would use the fact that at half neutralization, the pKa is equal to the pH. And that's because this ratio of A- over HA, the acid, will be equal to 1, because we've got the same amount of A- and the same amount of HA at half neutralization, because that's the definition of half neutralization, because we've neutralized the acid by half. And so we have that the pKa is equal to the pH, and so we can find the pKa, because that will just be 5. And then we can use this formula of pKa equals minus log to the base 10 of Ka. So that means that Ka is equal to 10 to the power of minus pKa. And so you get the Ka is equal to 10 to the power of minus 5, which comes out to be 1 times 10 to the minus 4 moles per decimeters cubed. But that's just an example. So you would get a different Ka for your experiment. Now I'm going to look at some questions. So for the first question, these titration curves are for combinations of different aqueous solutions of acids and bases. And all the solutions have concentration of 0.1 moles per decimeters cubed. Identify which graph is the following. So for A, they want the addition of 25 centimeters cubed of ammonia to hydrochloric acid. Ammonia is a weak base, and hydrochloric acid is a strong acid. And it's very useful to remember some of these weak bases, strong acids, strong bases, weak acids examples, because sometimes they will ask you about different chemicals without telling you whether they are weak bases and strong acids. So usually weak acids are the ones which are carboxylic acids, so organic molecules, and the strong acids will be the hydrochloric acid or sulfuric acid, nitric acid, those kinds of acids. The strong bases will be the hydroxides. So you have sodium hydroxide, potassium hydroxide, and you need to remember that ammonia is a weak base. And so what we expect with this graph is that it should start off at quite a low pH because we start off with the HCl before the NH3 is added. So we should have a very low pH to start off with. So right away we can rule out D, and then we can rule out A as well. So it's between B and C. So now we look at NH3. So NH3 is a weak base, and that means that the ending of the curve should be not very high, because the pH of a weak base will be closer to 7 compared to 14. And so it must be C. And then for B, the addition of 25 centimeters cubed of sodium hydroxide to ethanoic acid. So sodium hydroxide is a strong base, and the ethanoic acid, like all organic molecules, is a weak acid, sorry. And so we start off with quite a high pH and then end with a really, really high pH. And so it must be A. And then for C, we have nitric acid, which is a strong acid. And then potassium hydroxide, which is a strong base. So we have a strong acid being added to a strong base. And so it must be D, because this is the only curve where we start off with the base and we're adding an acid to a base. And so the answer is D.